who will discuss the structure with two halo nucleons. Dr. GrinyuK received his master's from the Taras Shevchenko National University of Kiev, Ukraine in 1975, and his PhD from the Boris Institute of the National Academy of Sciences of Ukraine in 1980. Subsequently, he joined the Boris Institute as a researcher. His scientific work deals with the quantum dynamics of Q-nuclear and Q-cluster systems, both analytically and numerically. So that's all from me. Dr. GrinyuK, please take over.
Thank you very much for your introduction. And I first of all want to thank for such a possibility to make a report in such a nice place for such nice participants. And let's start. I believe this is the first seminar. Maybe in the nearest future I'll organize another one. This one and the next will be united by the variational principle. Next time I'll tell you about some important physical problems which can be solved by analytical estimations using the variational principle. And now I'll speak about the precise calculations and the Fibonacci problem with the use of the variational principle. The plan of my report is the following. First, as usual, we start with the Hamiltonian, because it is one of the main problems in the nuclear physics, how to formulate the Hamiltonian, having small information about the nuclear forces. And then about the method, variational method, how we solve the Fibonacci problems. And I'll speak mainly about the 5 cluster systems: carbon 14, oxygen 14, and nitrogen 14, as consisting of 3 alpha particles and 2 additional nucleons. The details about more simple systems, lithium-6, helium-6, and 4 cluster systems, beryllium-10, carbon-10, you may find in previous publications a few years ago, made by myself and my colleagues. And today I mainly will speak about the problems which are printed just now. You see the 2nd of November this year as archive preprint. Mainly this material is carried out due to Bruno Kessler Foundational support and hospitality of the city. The details you may find in these publications. And now let's start. When we studied the structure of helium-6 and of lithium-6, they are very similar in their structure. And we were not first in this study. A lot of people studied these simple systems. They observed such an interesting thing that the ground state wave function, or the density probability in multidimensional space, contains 2 peaks which correspond to 2 different configurations. They are schematically shown on the left and on the right. When the 2-neutron subsystem and an alpha particle moves around the center of mass of the total system. And next configuration, when both subsystems have the central masses, which coincide with the central mass of the total system. These configurations were called a cigar configuration, cigar for smoking, and triangle configuration. When we started to study 4 cluster systems, 2 alpha particles and 2 extra nucleons, carbon-10 and beryllium-10, you may find this maybe one of the first study in this article. We also have found 2 configurations. And again, subsystems consisting from alpha particles and nucleons moved around the central mass of the system, or another configuration when the center of mass of subsystems of the total system coincides. The wave function, if will depict such a partially integrated squared wave function, we'll find 2 peaks. We may integrate over some of the variables in order it is difficult to depict multidimensional wave function. 2 peaks, like in helium-6 and lithium-6. And then we try to put the question, and what will be in carbon-14 and oxygen-14 and nitrogen-14, consisting from 3 alpha particles and 2 additional nucleons, whether they will have something similar structure, a similar structure with positions of the centers of mass of subsystems. The answer is yes, they also have 2 configurations in the ground state. But such naive picture is wrong. I will show further that twin-nucleon subsystem moves mainly inside the carbon-12 subsystem, inside, not out of it. First, we start with the Hamiltonian. For example, for oxygen-14, it looks like this, and you have a lot of Coulomb terms because protons have a repulsion, protons and alpha particles between themselves. You have a lot of terms. In case of nitrogen 14, a little bit less because we have this. There's a little mistake. No problem. Well, let's look at this Hamiltonian. And Coulomb terms immediately can be written down. This is. But what about the nuclear potentials? The proton-proton potential, just as the neutron-neutron potential, due to the symmetry of Church symmetry of the nuclear forces, would take in a simple form of 3 Gaussian functions, but we fit the parameters of this potential to reproduce the phase shift. You see, it is not bad. Points are calculated with a realistic potential, the best at that time, realistic potential, because experiments with neutrons are difficult to carry on. And you see our simple potential reproduces the phase shift, it reproduces the scattering length, and the effective range. Then we have to introduce a potential between a neutron and alpha particle. It is a more complicated story because simple local potentials, simple local potentials are not relevant. They contradict the theory, Levinson theorem. You see, the phase shift starts from pi, 180 degrees, and then decreasing. This means that you have one bound state, but a neutron and alpha particle do not form a bound state. This contradiction may be overcome by the so-called in literature non-local potentials with forbidden states. You see, in addition to local potential, it is our invention, another authors proposed, but we introduce additional separable term, which is non-local. And then the Levinson theorem is generalized, and we have simultaneously the phase shift and the fact that there is no bound states between neutron and alpha particle. This is a repulsive term. Parameters I can here. Maybe if you have questions, I'll say something additional about these potentials. The same P alpha potential. This is the phase shift and parameters of this potential. Similar potential for alpha particle. You see in this figure a comparison between the well-known Ali Budner as state potential blue line and our version with forbidden states. It is even better, but the main result is that there is no contradiction between Levinson theorem and the phase shift.
Just a curiosity, these are just in X wave. It's just X wave, this potential.
This potential,
in general, all the potential that you show is just the X wave, the reproducer of the phase shift of the X wave.
yes.
Okay.
Because it is the main.
Oh yes, sure.
But our potential, you see, it is an interesting one. If you take as a state, both terms are acting. If you take not the S state, then the repulsive term separable is not active.
Okay, that's okay. I was just.
Here are the potentials used for calculations, but the most interesting is the table in the bottom. We simultaneously fit the potentials in such a way that to reproduce the energy of the nucleus and its charge radius. it is maybe even more important than the phase shift. Because if we are studying the structure of the nuclei, we need to have correct asymptotics. It depends on the binding energy. And we have, when we study, for example, density of factors, we should have correct charge radius. But the problem is that for oxygen-14, there is no experimental value for the radius, because it is very rare isotope. It lives about 1 minute, and it is a gas. So experimentators have some problems to deal with such nuclei, and the charge radius is not measured, and our prediction is 2 and 4.4 Fahrenheit.
It is smaller than the.
Yes, this is an effect which you just noticed. It might seem that additional two protons make larger size.
Binding energy is smaller.
Yes, yes, but and the energy is small. But the effect I will show further lies in the following: the carbon-12 subsystem is almost unchanged, but the additional nucleons are moving inside. So the charge radius of oxygen-14 becomes smaller.
You know that they, sorry, just because we started this thing, that they saw the same thing in the calcium, that there is the spin and actually the proton is the inside, right? They look similar, this thing,
Yes,
to me.
yes.
It's very cool.
And we fitted potentials in such a way that we produce energies and only the charge radius of carbon-14. And then we obtain the result for potentials for nitrogen-14 are similar. We also reproduce the energy and experimental charge radius. And now, short question, maybe some remarks about how we calculated the phase shifts for such potentials with local and non-local part. Because in the book of Kolodjeva, variable phase approach, maybe you know this book, this question is discussed, and the equation for the phase shift contains non-physical singularities, because you see cotangent contains unknown phase shift, and in some points it may have singularities which are non-physical. It is a mathematical problem. And how do we solve this problem? We propose another approach. Maybe we were pioneers in this field, maybe or not, I don't know, maybe, but we invented this method to solve a system of the first order differential equation. They are linear, they do not contain cotangent, they contain sine and cosine, and no singularities. And you may find very nice. The same for the case when you have the Coulomb, additional Coulomb term, then you have in asymptotic Coulomb functions, but the method is very similar. In the case when you calculate the scattering length, this system becomes a little bit simpler. So I told you how we calculated the phase shift. You may find the details in articles. And now, yes.
And this approach works also for the multi-scattering problem, or just for like one channel,
One channel.
only for one channel,
One channel.
this channel.
Yes, we didn't consider. Maybe it may be developed.
Okay, okay.
Now, variational method, which we used for solving the Fibonacci problem, the 5-bit problem in our case. You know very well. You know very well the Ritz variational principle. Yes, E is less or equal, but more suitable is Galerkin method, which is also has the properties of variational estimation, but it looks like a system of algebraic equation. So it is the Schrödinger equation in another representation, in a representation of basic functions, which we choose. We choose basic functions which were proposed by Kukulin and Krasnopolsky and then some other authors, and very nice described in a book, very nice book, Suzuki and Varga, Stochastic Variational Approach to Quantum Mechanical Fibonacci Problems. They knew one another very nice, Suzuki, Varga, and Kukulin. So this is maybe was initiated by Kukulin and then. So what is the idea? The basis consists of a number of exponential functions of different size, different shape, and with respect to relative coordinates. And you may take a number of such Gaussian functions. And next slide will show you the convergence of this method. It is not the 5-particle problem. It is tritium, helium-3, and helium-4 problem. But the convergence is of the same type. You see for different potentials, you are starting at a different place because strong repulsion make problems even for the ground state sometimes, yes, when you take a simple wave function. But when you take a sufficient number of functions, then you rapidly go to the answer. In our calculations, we took about from 300 to 500 functions. And with the count of symmetrization with respect to identical alpha particles and identical to Nucleons, the number of wave functions, basic functions, is even more. And then after variational procedures, you find the wave function in a very simple form as a set of expansion in Gaussian functions. And then you may use this function in explicit form and calculate anything. For example, you may calculate the root mean square radii, relative distances. By the way, in the bottom you see a very nice formula which connects relative distances and root mean square radii. It looks very trivial, but very useful. And for example, for carbon 14 and oxygen 14, we have relative distances and radii. In particular, for oxygen 14, they found the charge radius 2.41. But if we are speaking about the mass radius, you see the last but one column, then the radius of oxygen 14 is greater because the energy is smaller. And the charge radius, another story, because carbon 14 has nucleons instead of protons. The same for nitrogen 14, we calculated, and now we are going to form factor. Here you see form factors for beryllium-10 four-particle system. I simply want to explain what is will be depicted in the next picture. This is picture more simple. You see, in Helm approximation, well known, yes, a form factor of beryllium-10 is simply a product of form factor calculated for point-like particles, and then multiplied by experimental form factor for helium-4, for alpha particle. This is a minimal taking into account of the fact that alpha particle is not a point-like. And you see in the picture, red line, two dips. The first dip is due to the first multiplier. This is a factor of a three-particle system. And the second dip is due to the helium-4. The same for carbon 14. You see a little bit more dips, but green line, this is the helium-4 alpha particle experimental form factor. And the second dip in charge form factor of carbon 14 is due to helium-4. And the rest are due to this five-particle system. And what about charge form factor of oxygen 14? We have two terms in Bohr approximation, because protons are also make a contribution. And the second term, due to the protons, smoothen the dips of the first term. So the red line is the oxygen 14 charge form factor. It has no dips. Density distributions. You see the dashed lines. They are the density distribution multiplied by r squared. Just r squared multiplied by density distribution is a probability density. And you see red dashed line depicts the density of protons, neutrons, sorry, carbon 14. The same will be for oxygen. Neutrons and blue line for alpha particles. You see that extra neutrons move essentially more close to the center. And this is the same for density distributions. We can also calculate pair correlation functions. This is the probability density to find a pair of particles at a definite distance. The dips at the beginning are connected with repulsive terms in the potential. The percolation functions reflects to great extent the behavior of the potential. Their maxima are bound with the minimum potential and vice versa. We can also calculate the momentum distributions. If we have the wave function, we can calculate everything. You see that extra neutrons or extra protons in these nuclei have specific dependence with a dip. You see, we have low energy contribution and high momentum, high transfer momentum contribution. This corresponds to two configurations, which I will show further. While the alpha particles, more or less smooth dependence. By the way, you see the average kinetic energy of neutrons or protons are about 4 or 5 times greater than the alpha particles, mainly because they are very heavy. Alpha particles are 4 times heavier, and they move slowly as compared to. Now I depict 2 peaks of the wave function after integration of the rest variables. Here are the relative distance between the neutrons, for example, or protons, and the relative distance between the 2 neutron subsystem with respect to the center of mass of carbon-12. And you see 2 configurations. It depends on the angle between the vector r and rho. Here you see a more detailed picture. Theta 0, 30 degrees, 45 degrees, 90 degrees. The peak depends on the angle. And now I'll speak about the excited states. You see the lowest spectrum of both nuclei, and we started the ground state, but we also can calculate excited states. We're studying the lowest one, 0 plus excited states. These are details, but we see that the excited energy was not, we did not fit the potential, but you see that excited levels are reproduced rather good. Experiment and calculations coincide with reasonable accuracy. And in the excited state, the radius of oxygen-14 is now not less, but of the same size, but even a little bit greater than in carbon-14.
So sorry, just a question. To calculate the excited states, we use the same variational procedure
Yes.
by imposing the, I don't know, the condition of orthogonality between the ground state.
Yes,
and,
yes, this is necessary in Ritz method. Yes,
Okay.
but we used a Galerkin method. The spectrum of this system of algebraic equations is simply the spectrum of physical systems. And becomes more and more accurate if you spread the basis. So this, very comfortable method, GrinyuK method. Density distribution pair correlation functions. Well, I maybe list some of pictures. Momentum distributions, they're different, of course, in excited state and in ground state. And here are the pictures similar to that shown below, but like a map, not like hills, but like a map. You see that the probability density concerning the two Nucleon subsystems drastically changed when we come from ground state to excited state. They are the maxima rearranged, and the shape is changed. And when
They are almost orthogonal, at least to my, because one was being like on the diagonal and the other one is in the other diagonal. I don't know, maybe I'm wrong. The excited state and the math looks like orthogonal one to another.
maybe.
I mean, it looks like it because they are.
Yes, they should be orthogonal.
Yes, so they are somehow, okay, sorry, just put problem.
And when we study the rearrangement of peaks, when we take two alpha particles and their center mass with respect to helium-6, then we see that almost nothing changed. This means that excited state is not the excitation of alpha particle subsystem, but of Nucleon subsystems. They are moving in the field of carbon-12 and have ground state and then excited state, and the configuration is changed. And what else? We have calculated not only elastic form factors, as you have seen above, but also transition form factors. Transition form factors differs from the elastic one only in the right bracket. Instead of the ground state, another state, excited state, and then Helm approximation is the same. And we have similar picture, no dip in oxygen 14 and the dip in carbon 14 due to helium-4. This is a symbolic picture of these systems. The two Nucleons move more rapidly and move mainly inside. This movie is made by my son Alexei. I cannot make such picture. He helped me to make this movie. I'll omit the coefficients of clusterization. I only say that this method enables one to look even asymptotics of the wave function and find some important things like nuclear vertex constants and so on. And conclusions you may find here. And thank you very much for your attention. And one more announcement maybe I'll make. As you have seen above, half of my publications were in Ukrainian Physical Journal. And I invite you to publish your articles in the Ukrainian Physical Journal, because now we have some problems. For example, this year our institute had to carry on a conference, New Trends in High Energy Physics. This conference, as usual, gave to our journal about two issues of articles. now we have now. And Ukrainian scientists have some problems that they also make less contributions. We have lack of articles, and we invite you to help and to submit articles to this journal. It is free access, peer-reviewed journal, free publication. And so you may have both hard copies in your library, and in internet you may find your articles at corresponding sites. So it is very, very useful. If you are deciding what journal to choose, please, you're welcome. So thank you very much for your attention.
Thank you, Boris, for this very nice talk. I would like to invite questions now from both the local audience as well as online.
Sorry, can I ask?
Yes.
It's interesting. Here you have internal alpha particle clusters in carbon or oxygen nuclei. Did you try consider, for example, magnesium 24 with multi-alpha clusters? That is where each cluster may consist of some alpha particles. Thank you. Also, not magnesium 24, for example, here oxygen 14 with 2 alpha particles plus 2 alpha particles and plus 2 nucleons.
Well, thank you. We are going to consider more complicated systems. We are going to, but it is not considered yet.
Okay, okay.
Thank you.
I can go ahead if there are no other questions online. I have a lot of curiosity, actually. The first one is, so when you construct the wave function, you said that you are anti-symmetrized.
Symmetrized with respect to alpha particles.
Okay, yes, symmetric and anti-symmetric with respect to the neutron and protons, or do you?
No,
Okay.
no, only symmetrized with respect to 2 neutrons or 2 protons. If it is nitrogen 14, we do not symmetrize proton and neutron.
Okay. The other are actually curiosities. So since you mentioned before that you compute lithium 6, I was curious if you compute the particle moment of lithium 6 with you know, the particle moment is very hard to get with lithium 6.
Yes, but no. I believe it is necessary to take into account tensor forces.
Okay. I was just curious.
But we did not.
Yeah. Okay, that's very cool. That's all. Thank you very much.
Thank you for your attention.
Sorry, I'm not so familiar about, but I have a very maybe naive work. You talk about 2 methods. One is nuclear system, and second is alpha system, right? I want to know, is these 2 systems can transport, like decays, one system decays to another system, or transport?
Generally speaking, yes, but this is a model. This is a model. Alpha particle is tightly bound. 28.3 MeV the binding energy. It is too large when we considering the ground state and small excitations. It even do not polarized. So this approximation is very nice. By the way, Kukulin has shown that very, very beautiful function for example, for helium-6 or lithium-6 is the obtained function multiplied by the function of helium-4 of the alpha particle. And this is very nice approximation. So in our model, it is hard, but in principle, you may consider different combination, especially for high excited states.
Just another curiosity, very technical, but can you do this kind of calculation on your laptop?
Yes.
Okay, it's very easy to, okay, it's not very heavy.
Yes, only time consuming when you find the variational minimum with respect to nonlinear parameters, you will.
Yeah, that's probably.
Time consuming, but it is very easy.
But the matrix elements are easy to compute because they are all Gaussian, right?
Any more questions? Also online? If not, let's thank Boris again and see you all.
Thank you very much.